Dear students, continuation to the array and its types. In the previous session, we discussed about the broadside array and I explained about how to derive the expression of the side lobes, beam width, the nulls and beam width between nulls from the array factor. But in this session, we are going to discuss about the broadside array, then how to derive the expression of the maxima, nulls, side lobes from the array factor, and also what are the differences between the broadside array and the endfire array and parasitic array, as well as I am going to cover thin linear antenna in this session. So first we'll look the endfire array. The physical arrangement of the endfire array is same as that of the broadside array, where the current supplied to the elements will be same, means the magnitude of the current flowing in each element is same, but there is a phase difference of current in each element. And in the endfire array, the direction of the radiation is not right angle to the plane of the array, and the radiation pattern of this endfire array is unidirectional. The major lobe is at one end, which means that the maximum radiation which present at one end, and the minor lobes which represents the losses. Okay, so also here I shown this bidirectional radiation pattern of the endfire array, but the major lobe which is which occurs at only one end, where the maximum radiation is present. So next, how to find the maximum? So maximum radiation occurs for xi is equal to 0. So as you know, xi is equal to beta d into cos pi plus delta. Delta is the phase angle. Then xi becomes xi is equal to 0 means beta d cos pi plus delta is equal to 0, which implies beta d cos pi is equal to minus delta, and cos pi is equal to minus delta by beta d. When pi is equal to 0, cos 0 is equal to 1, which implies that minus delta by beta d is equal to 1. That implies delta is equal to minus beta into d. Now substitute delta is equal to minus beta d in the expression of the phase difference. You will get xi is equal to beta d cos pi minus beta d, and take beta d common outside. You will get the phase difference for the simple endfire array is beta d into cos pi minus 1. So now we are going to find out side lobes. What is the expression for the side lobes? So like the previous array type, that is a broadside array, here also we can find the side lobes by equating the numerator of the array factor to unity. Dear students, numerator of the array factor is sin nxi by 2 equate to 1. Then nxi by 2 is equal to sin inverse of 1. Sin inverse of 1 means either 90 degree or 270 degrees. So nxi by 2 is equal to 2k plus 1 into pi by 2. So 90 degree and 270 degree can be expressed as 2k plus 1 into pi by 2. So from this we simplified and evaluated xi as plus or minus 2k plus 1 into pi by n. 2 get cancelled, and we can find out the phase difference xi as 2k plus 1 into pi by n. But what is the phase difference? We derive the expression of the phase difference from the maxima, that xi is equal to beta d into cos pi minus 1. Equate this to 2k plus 1 into pi by n. Then you will get cos pi minus 1 is equal to 2k plus 1 into pi by n into beta d, or cos pi is equal to 1 plus or minus 2k plus 1 into pi by beta d into n. Then pi becomes equal to cos inverse of 1 plus or minus 2k plus 1 into pi by beta d into n. So next we are going to find the nulls expression. So to find the expression of the nulls, we should equate the numerator of the array factor to 0. Sin nxi by 2 is equal to 0 indicates that nxi by 2 is equal to plus or minus k pi, because sin inverse of 0 is either 0 degree or 180 degrees. That can be expressed generally as plus or minus k pi, where k is equal to, when k is equal to 0 means then nxi by 2 is equal to 0, or k is equal to 1 means it should be equivalent to 180 degrees or pi. So from this, from the above expression, we simplified the xi value as plus or minus 2k pi by n, but the phase difference xi is equal to beta d into cos pi minus 1. Equate this to 2k pi by n. So you will get cos pi minus 1 is equal to 2k pi divided by n into beta d, or cos pi is equal to 1 plus or minus 2k pi divided by beta d into n. Then find out pi as cos inverse of 1 plus or minus 2k pi divided by beta d into n. So this is the expression of the nulls using the array factor. So next we can find the beam width between nulls. Nulls are given by pi is equal to plus or minus cos inverse of 1 minus 2k pi divided by beta d into n. When k is equal to 1, we will get the pi dash. Pi dash is equal to pi naught by 2. Is it right? Pi dash is equal to pi naught by 2. So then you will get pi naught by 2 means plus or minus cos inverse of 1 minus 2 pi by beta d into n. Then pi naught becomes 2 into cos inverse of 1 minus 2 pi by beta d into n. Beta d into n. Please note down, this is the beam width between the nulls. So when n is very large, pi naught is equal to 2 into root of 2 into 2 pi divided by beta d into n. Since beta is equal to 2 pi by lambda, then beam width between nulls, pi naught is equal to 2 into root of 2 lambda by n into d. So this is about that's all about the end fire array. So next is collinear array. Collinear array is a broadside radiators in which the direction of the maximum radiation is perpendicular to the line of the antenna, and also you are observing in the collinear array that all the antennas lying along the same line. That is called as a collinear array, and all are vertically arranged. Then radiation pattern is seems to be the figure of H. So next is parasitic antenna array. So the element supplied power directly from the transmitter, and for receiver in case of receiving the antenna is called driven element. Suppose if the elements are not supplied power directly, they are called parasitic elements. So parasitic elements means the elements which are not supplied power directly are called parasitic elements. The array, antenna array, which consisting of the parasitic elements is called parasitic antenna array. Next is a thin linear antenna, so which consisting of the short dipole where the diameter is very much small compared to the length, but length is also small compared to the wavelength. So overall the diameter is very small compared to the wavelength. So in the thin linear antenna we are going to derive the expression of the field component E theta and H pi. To derive that, so we have to write the retardation current I is equal to I naught into sine of 2 pi by lambda into L by 2 plus or minus Z and exponential of j omega into t minus r by c. So in the above equation, the function or the term sine of 2 pi by lambda into L by 2 plus or minus Z is the form factor for the current on the antenna. In this function, the term L by 2 plus Z is used when Z is less than 0, and L by 2 minus Z is used when Z is greater than 0. Then the far fields dE theta and dH pi are the distance from the infinitesimal dipole dz, or dE naught is equal to j into 60 pi into high sin theta dz divided by s into lambda. dH pi is equal to j into high sin theta dz by 2s into lambda. We can find E theta from the relation z into h pi. Z is equal to 120 pi is the intrinsic impedance of the uniform plane. Then E theta is equal to 120 pi into h pi. So by finding the h pi, we can determine the electric field along the theta direction. First find out what is h pi. H pi is the far field component along the pi direction. This is far field component related to magnetic field, matter statics, that is magnetic field which is in the direction of the pi direction, which is the direction of the pi. So first find out h pi. So what is h pi? H pi is obtained by integrating dH pi. So now substitute the value of the dH pi and substitute the retardation current, and substituting s is equal to r minus z cos theta and beta is equal to 2 pi by lambda. The equation of the far field h pi is simplified as j into I naught by 2 pi r into cos of beta L into cos theta divided by 2 minus cos of beta L by 2 divided by sin theta. By knowing this the far field component along the pi direction, we can find the field component along theta direction very easily using the relation z into h pi. Z is the intrinsic impedance which is equivalent to 120 pi. Then E theta becomes 120 pi into h pi. then E theta becomes 120 pi into H pi is J into I naught by 2 pi R into cos of beta L cos theta by L minus cos of beta L by 2 divided by sin theta. By simplifying that, you will get E theta is equal to J into 60 into I naught by R into cos of beta L into cos theta by 2 minus cos of beta L by 2 divided by sin theta. So these are the far field equations of the the thin linear antenna. So thank you for watching the video.